So last time we were talking about center of mass. And we talked about how to find it for a discrete number of particles when those particles could be treated as individual little things. So you could think about pool balls or marbles that were spread out, and each object would have an x and a y coordinate. And then we could figure out what the center of mass was from there. We also talked about finding the center of mass for a continuous distribution of mass. So finding the center of mass of U, for example, or a pad of paper, or a basketball. And we kind of had a vague formula. We talked about integrals, but we also talked about how in many cases when we have an extended object or a continuous object, we could use symmetry or geometry to figure out where the center of mass is. So we talked about how if we had a sphere, where's the center of mass going to be? Right in the middle, okay? And the same thing really works for any object that's symmetrical. So for instance, as we'll see in the next problem that we're going to do, if I have some kind of a block or a slab, as long as the density of my object is uniform and the object is symmetrical, then the center of mass of that object will be in the middle. And we did a problem last week where we found the center of mass of the Earth-Moon system. And part of what we did was consider that the Earth and the Moon were both uniform objects as far as density was concerned. We know they're not, but it was an assumption that we made. And then we assumed that all of that mass was concentrated at the center of mass, which turned out to be the middle. Okay? And then I treated it as if it was two discrete particles. Okay, and found the center of mass using that formula that we had. So we're going to do another problem right now that's kind of the same thing before we move on. So let's do page 246, number 3, if somebody would read that for us, please. Isn't D1 11? Oh, okay. I thought you said 10. I'm sorry. My bad. Okay. So we've got our slab here, and our slab is made of two different things. So there's going to be the aluminum side over here and the iron side over here. And we have dimensions. We know that this is 13 centimeters. These are 11.0 centimeters. And this height is 2.80 centimeters. So, just as we considered the Earth and the Moon to be uniform objects, like we said a few minutes ago, and we found their center of masses using symmetry and geometry, I can do the same thing here. Does the whole slab have a uniform density? No. But what do you think about the iron half? So its center of mass would be in the middle. Okay, so the center of mass of the iron will be in the middle of the iron, and the center of mass of the aluminum will be in the middle of the aluminum. Yeah, and then what I do is basically I change the problem into where I have 2 point masses, where all the mass of the iron is located at the iron center of mass, and all of the mass of the aluminum is located at the aluminum center of mass. Okay, makes sense? Okay. And this is because we have a uniform mass distribution for each substance. That's very important. If it's not a uniform mass distribution, then I can't use this trick. Okay. So let's look at the iron half first. And remember, when we were talking about center of mass last week, we said we could use that vector r, which would be a position. And that r center of mass would give me the position of the center of mass. So if it's going to be in the middle, I'm going to want to find the x coordinate. But in order to find the x, y, and z coordinates of the center of mass, what's missing from my picture? Axes. Okay? So I'm going to let my origin be down here in this bottom corner. So that's going to be plus x. Plus y goes back that way. And plus z goes up. It has to go that way for a reason that will become apparent in a few chapters. So, what's my x coordinate for the center of mass of iron? Yeah, it'll be 11 over 2, or 5.5 centimeters I. How about for the y direction? Yeah. Because again, it's going to be half of this distance. And then 1.40 centimeters for k, because again, it's going to now be half of this distance. Okay. Now, when I'm finding the center of mass of a system of particles, I need to know where each particle is, and that's certainly helping me with this. But what other piece of information do I need? The mass. So how am I going to find the mass of that slab? Okay, so density in general is mass over volume. So what's mass going to be equal to? Density times volume. So if I need to find the mass of the iron slab, it's going to be the density of the iron slab times the volume of the iron slab. How do I find the volume of a slab? Length times width times height, right? Okay, so my density is what? That's the 7.85 grams per centimeter cubed. And then I'm going to have 11 centimeters times 13.0 centimeters times what? Thank you. 2.80 centimeters. And so what are we going to end up with for the mass of iron? Eh. Eh. Well, I think we're going to leave it the way it is for right now, because I have about 3 figs running around, but this is an intermediate answer, and I'll save my rounding for the end. Can I leave it in grams, or do I have to convert it to kilograms?
Well, you can leave it in grams.
Why can I leave it in grams, Priya? I'm going to leave it as grams because they're all going to cancel, right? My gram, because it's going to be m times x on the top. Well, yeah, and I'm solving for the x center of mass. So the grams are all going to cancel out. And it's, while this is a, one would hope, very simple conversion, you could mess it up. Okay? So if you don't have to, don't do something. All right, so we're going to leave this here. And then we need to do the same thing for the aluminum. So we have to find our center of mass, aluminum. And what's the x value going to be? Really? It might be 5.5 from here. Right, because if I'm measuring my center of mass from my origin all the way over here, there's a whole 11 centimeters that I have to add. Yep, so it'll be 16.5 centimeters I. Right, I don't have to, my J value will be the same. And my K value will be the same too, because I don't have that extra width of a slab when I'm talking about my Y and Z directions. Right? What else do I need? Right, I need the mass of my aluminum, which I can find the same way. The density of the aluminum times the volume of the aluminum. The volume of the aluminum is the same as it was for iron, but I believe my density is 2.7 grams per cubic centimeter. And then the dimensions of my slab are the same. Okay. So what do we got? Okay. So 1,081 grams. Right? We good? Okay. So now I can think about the problem like this. Here's my origin. Here's going to be my mass of iron at x equals 5.5 centimeters. Here's going to be my mass of aluminum at x equals 16.5 centimeters. And the x and the y values are the same. I'm sorry, the y and the z values are the same, right? So how do I find the x center of mass coordinate for the whole system now? I don't just add their x values. Their x values have to be weighted by something. Yeah. So it's M iron, x center of mass iron, plus M aluminum times x center of mass aluminum all over the sum of the masses. Remember, we talked about how those x values are weighted by what the mass was, and that the center of mass would always be closer to the most massive object. Okay. So that gives us 3143 grams times 5.5 centimeters plus 1081 grams times 16.5 centimeters divided by 3143 plus 1081 grams. And what do we get for the x center of mass? So what should our sig figs probably be? No, you can leave it as centimeters. Everything in the problem was, well, you really want to make it 8.3 because here's where kind of the different way of dealing with sig figs comes in. Most of the numbers, and certainly the two numbers that you're adding right now, only have values out to the 10th place. So to assume that you know an answer accurately to the 100th place is presumptuous. Okay? There's no way that you really know what that's going to be. Okay? And how about the y center of mass? What's that going to be? What? Yep, 6.5. How does Casey know that it's 6.5? It's the same for both objects. They're already along a line in the y direction. It's even though it looks like these center of masses are in different places, if I was only looking at the y direction, they're in the same spot already. And the same for the z value. Yep. Oops, not x again. Here, you can have the 0 because that original value was 2.8. Okay. All right. We good? We got it? Okay. I just want to go over a couple more things, and then we'll take a break for a couple minutes, and we'll go through the break homework. Okay. But the next thing that I want to talk about is linear momentum. Now, momentum in general is often referred to as inertia in motion. Mm-hmm. And if you think back to Newton's first law, which is the law of inertia, and what does the law of inertia tell you? Objects. Right, an object at rest will stay at rest unless acted upon or until acted upon an external net force. So when you think about momentum, you want to think usually about something that's already moving. And momentum kind of has to do with how hard it is to change the motion of something. So if something has a lot of momentum, it's difficult to change what that object is doing. So the two examples that I like to think about are, not that I like to think about it, but one is a high-speed bullet. Okay? So you've got something that's very tiny, but is moving at a really fast speed. And what happens to that bullet if you're shooting it on a range? What's it going to do? It might hit a target. Is it going to stop in that target? Maybe, maybe not. Sari's saying no. What if that target's paper? Is it going to stop in the paper? No. Okay. Is it going to stop if you put a whole phone book of papers? Maybe, maybe not. What if you put a piece of wood? Maybe, maybe not. Okay, so to change the motion of that object is going to take a lot of work, and you can take that the physics way and the real world way. Can a phone book stop a bullet? Yeah, it depends on the speed of the bullet, definitely. It depends, it honestly depends on the speed of the bullet. Okay, and you will actually do, we don't do this in class, although you may do it in, when I taught at the College of Worcester, we shot a rifle into a bullet and measured how far the bullet, we shot a bullet into a block of wood and measured how far that block of wood moved. But like the whole gun was encased in like a box, and it was crazy. All right, so that's one way of looking at it. Another way of looking at it is my favorite heavy grocery cart. Okay, so again, place yourself at the Amherst Street Wegmans, and you come out of Wegmans, and you're doing a huge shopping trip for whatever reason. So you've got a 20-pound bag of rice, you've got 20-pound bag of potatoes, 20 pounds of potatoes, a couple of frozen turkeys, lots of canned goods. It's a very massive cart. And you start to push that cart, and if you ever go to the Amherst Street Wegmans, when you come out, there's that incline. When that cart starts going down that incline, and your car's right there, think about how hard it is to try to divert that cart, to try to change the direction of that cart. Is it moving very fast? No. How fast can I make a cart move? Seriously. Okay? But it has a lot of mass. So in both of these situations, the object has a lot of momentum. And so that tells us that momentum, which is a vector, is equal to mass times velocity. So this P here is momentum. And that V is in fact velocity. which means that I can have a momentum in 2 or 3 different directions. Okay, and that I can treat that momentum separately in each direction. And another thing that momentum is really good for is, I like to think of it as bookkeeping, is keeping track of what's going on. So as Priya noticed, I brought out my Newton's cradle. And momentum is what tells me that if I raise up one ball is going to come out on the other side. Momentum also tells me that if I raise two balls are going to pop up on the other side. Mm-hmm. Yeah. Yeah. Ford tends to devolve faster because there's more friction. Okay? So this is more conservation of momentum. And we'll come back and we'll talk about that maybe later this week. All right? But for now, we just want to talk about the concept of momentum. So I want to do just a couple of examples about momentum. Really, again, kind of the plug and chug, let's get used to the formula kind of thing. And then we're going to talk very briefly about Newton's second law. And then we'll be done. And tomorrow we will start, oh no, tomorrow's the quiz, right? And then when the quiz is on the rest of chapter 8. And then Wednesday or Thursday's drop day. And then I think Friday we will start impulse, which is the next step in understanding momentum. Okay. All right, so let's do sample problem 17. If somebody would read it for us, please. Sure, you could read B. Okay. So, I've got my little VW bug here that has, it's a big mass compared to a person or a basketball, but compared to a Cadillac, which don't really look like this anymore, but they used to. It used to be the thing about a Cadillac is it had a really long hood and it often had a really long trunk. All right, but my Cadillac weighs more than 3 times, or I'm sorry, it does weigh, but it in fact masses more than 3 times than my VW Bug. And it has some speed, which I could turn into a velocity, which is 16 kilometers per hour. And we'll see. Now that you know how to do it, I don't have to worry about it as much. Okay. So if I want them to have the same momentum, and we'll assume they're moving in a straight line along the x-axis because I can put the x-axis in any direction I want. What do you think about the speed of the VW Bug? Is it going to, what? Yeah, it's going to have a greater speed than the Cadillac because it has what, Maddie? Yep, because it has a smaller mass. Okay, so let's start by figuring out what the momentum of the Cadillac is. And momentum has no units of its own. Like the units of energy are joules, The units of force are newtons. The units of momentum are really just kilogram meter per second from the formula. So I'm just going to leave this in kilometers per hour because I'm going to want to compare it. I want to compare my final answer to what the Cadillac's doing anyway. Okay? So the momentum of my Cadillac P2 is going to be equal to m2v2. Those are all magnitudes because I've only got motion in one direction. So this is a pretty simple plug and chug. And what do we get? Bless you. What'd you get? Yeah, which is a stupid unit. And if you were doing a real problem, you'd convert it and you'd have kilogram meters per second, which would be the SI units for momentum. But because it doesn't have a funky name, it kind of doesn't matter. All right, is that what everybody got? Okay. So I want P1 to be equal to P2. And P1 is going to be M1V1. And P2 I know is 42,400. What do you mean English? Oh, okay. So the mass of my bug is 816 kilograms. I want to solve it for V1. And what's V1 going to be equal to? Is that what everybody got? That's what Sarah got. Okay. Which is about 30 miles an hour. Good. What? Because it's going, yeah, about a third. A little less than a third of the speed. Okay. All right, so now we're going to take a flashback. And we need to ask ourselves, how fast does the VW Beetle have to go so that I get them to have the same kinetic energy? So I want kinetic energy 1, which is the Beetle, to equal kinetic energy 2. So what's my formula for kinetic energy? Now, would you expect that the Beetle is going to be going that 52 kilometers per hour and that's going to give them the same kinetic energy? No. In order to have the same kinetic energy? Well, because they have different masses. Okay, so of course I can cancel my half. The mass of my Beetle is 816. I'm going to solve for V1 squared. The mass of our Cadillac is 2650 kilograms. And the speed was what, 16 kilometers per hour? Squared. So what do we get for the speed of the Beetle? Okay. So how many sig figs do we have? Hmm.
We have two. So it would be 25.
Kilometers per hour. Is that what other people got? Okay. So this was really just momentum in one direction. Okay. So the next problem that we're going to talk about is going to talk about momentum as a vector. So let's do page 248, number 22.
Major 947 for some kilometers. You have to by a 0.165 kilometer cue ball as it bounces from the rail. The ball's initial speed is 2.003 meters per second. The angle theta 1 is 30 degrees. Ball's bounce reverses the y component of the ball's velocity, but does not alter the x component. What are the a angle theta to do, and b the change in the ball's linear momentum in a different location?
Okay. Correct. I was waiting for that part. All right. So, in fact, I don't really think it needs to be quite that big. So here's my ball. It's going to move in that way. Bounce off the wall. And come back off. Right? Okay. And I believe that we know this angle of incidence, right? 30 degrees. Okay. And we're told some things about the velocity, right? So if I make some axes here, and we'll let kind of up be y, or be positive y, and positive x to the right. Then, for instance, how would I write the initial velocity? How do I always write a velocity if I'm breaking it into unit vector components? I might say like Vxi plus what? I don't have his, okay, so I don't have to worry about that. Okay. So this is going to be my V1. And if my V2 is after the bounce, how do I write that?
Well, it says that it has the same
Yep. Nope, I know exactly what the y, so it's negative Vy times J. Okay. So if I let this whole line here be V1, okay, then this is going to be Vx, and this is going to be Vy, right? Okay. And here's my V2. So what's this going to be here? That's going to be Vx, and then this is going to be negative Vy. Okay, but the same magnitude, the same length. So part A wants us to find this angle over here. Yes? Okay. Do you remember what that angle should be? It should be the same. The angle of incidence should equal the angle of reflection. It doesn't just work for light. It should really work for anything. Yes, it is. Yep. I love Cyber Chase. Big fan. Big fan. All right, so I'm going to focus on the before. So tangent theta is going to be equal to what? I don't want a value. I just want to know what it is from the triangle. Here's my theta up here. Vx over Vy, right? Opposite over adjacent. All right. So let's call this angle alpha, just because we have to give it a name. Okay. So what's the tangent of alpha going to be? Vx over Vy. We could stick a negative sign in there, but that's just going to tell me what quadrant it's in, and I don't really care. I just want to know what its magnitude is. So what does this tell you about theta and alpha? They're equal, or at least their reference angles are equal. And being that I'm dealing with an angle that's less than 90 degrees, that's the angle that I want. So this tells me that alpha is equal to theta is equal to 30 degrees. Okay. As you suspected. And we are, of course, bouncing off a flat surface. We are, of course, measuring with respect to the normal and all that jazz. Okay. All right, so what does part B ask us to do? Okay, so what's the momentum before going to be? Okay, but it's the same m, so actually I can just make it m v1. And if I have to express that in unit vector notation, what am I going to write? Well, I've got to multiply by m again times the vyj. Okay. And I can write a similar expression for the momentum after the collision with the wall. It's going to be mv2. And how am I going to write that in terms of unit vector notation? Yep, because it's delta P, P2 minus P1, P after minus P before. So that's going to be M Vxi minus M Vyj minus M Vxi plus M Vyj. Well, hang on one sec, and then you can simplify it for me. I just want to say that remember, since unit vectors don't come up all the time in our lives, that I only add the x components to the x components, and I only add the y components to the y components. So Zoe, what were you going to say it reduces to? Okay. Yep, we're going to have MVXI minus MVXI. And remember that this minus sign is going to distribute to the MVYJ and give me two of those. Okay. So you may remember freshman year when we talked about the difference between the pain level when something bounced off your head versus something breaking on your head. There was a worksheet that had to do with it, and in one of the pictures the flower pot comes down and breaks, and in another part the flower pot comes and bounces off. When the object bounces off, that whole y momentum that's coming in has to be turned around and sent off. As we're going to find out on Friday, which is the next time we'll talk about any of this, this is going to be proportional to the magnitude of the force between the object that's bouncing and what it's bouncing off. And as you can probably guess, more force means more pain. So when the object bounces, when the object bounces off your head, it'll actually hurt more than if the object falls and breaks.
But that's why it really hurts to get hit by a shopping cart.
Sure.
Force is just the same.
No. Shh. What are you saying, Maddie? Yes. The whole reason that you're wearing a helmet is, well, it's the same reason why if your car is out of control, you drive it into a haystack as opposed to driving it into a concrete wall. Okay, is because driving it into the haystack increases the amount of time that it takes for that change in momentum to happen. And what actually happens is this is actually proportional to the force times the amount of time it takes for that change in momentum to happen. So the whole point of the helmet is that it has that it has that foam packing in it. And so that packing makes the change in momentum last for longer as the foam compresses. And so because you're increasing delta T, F can be smaller. That's also why you're safer in a car that has a bigger front end. It's probably why you're safer in that Cadillac than in that VW Bug, because if you hit something, that whole front of the car is going to compress before you compress. Probably, although that has a whole bunch of other issues. But yeah, which yes, exactly. Tiny smart cars are awful then because there's nothing to crush around you. So yes, exactly. That golden period between seatbelts and before we realized that gas guzzlers were going to use up all the gas, when we had those really big cars but everybody wore seatbelts, because that was a big thing too. I would guess that you were a lot safer driving around. If your parents were going to buy you a car, they probably wanted to buy you a car that was a little bit bigger so that you had protection around you. And that's what airbags do now. Airbags, again, are increasing the time that you change your momentum so that the force is less. And we'll talk about this again on Friday, because this delta P is actually impulse, which is J. And we'll put it all together. Okay? All right, so I want to talk about one more thing, just because it's kind of random, I guess, which is connecting momentum and Newton's second law. So you should have read about part of this. What is Newton's second law? F net equals ma. Okay. And what's momentum? P equals mv. Okay. So what's always another way I can write acceleration? The derivative. Okay, so you can always write it as dv dt. So if I go back over here to my equation for momentum, if I take the derivative of both sides, then I've got dp dt is going to be m times dv dt. Because technically, yes, my mass could change, but that's just not really something that happens. So we're not really going to worry about it. Yes, we will do the rocket problem at the end of conservation of momentum, which is one of the 3 hardest things that we do. We've already done one, which is change of reference frames. It's not quite like that. That would be a lot easier. It's more about the exhaust is going out, so the change in momentum is continuous. You're continuously expelling, the rocket is continuously expelling exhaust, and it's actually a conservation of momentum thing that makes the rocket go in the opposite direction. We are not really dealing with the pull of gravity in a situation like that. We're taking it out into the middle of nowhere because it would be too complicated to deal with gravity as well. And we're also not talking about the situation where the gas tanks are falling off. We're talking about the situation where the gas tanks are still expelling exhaust. Okay, so before those fall off, because that, honestly, that's easier. If the gas tanks are falling off as one thing, that's a lot easier to deal with because it's there one minute, it's gone the next. And a big part of conservation of momentum is defining the event that you're comparing the momentum to before and after. All right, so can you see where I'm going here? Where am I going, Maddie? Yeah, I've got m dv dt here and m dv dt here. So that's going to tell me that F net is equal to the change in momentum over time. Okay? Which, if you think back to that problem that we just did, we had the change in momentum was proportional to the force times the time. Okay? And the last thing that I really want to talk about, lickety quick, is that if you have Usually we talk about the momentum for some point particle or something that we consider to be a point particle. So if I'm going to talk about the momentum of a car, I'm assuming that the car is a uniform mass and I'm talking about the center of mass. Okay. However, if I have a whole bunch of particles, whether they make up a blob of water or a notepad or whatever, I can still talk about the total momentum of the system as being the total mass of the system times the velocity of the center of mass, wherever that may be. Okay. Which will kind of be a little hand-wavy as we go on. Okay. So I'll give you like a 2-minute break and then we'll start going over the winter break homework.